students. How are you doing? And I hope this unusual and crazy time finds you as happy and as healthy as you can be. Remember, nothing I'm giving you is required. Everybody handles stress differently, so some people may want to keep busy, some people may not want to think about school at all. Whatever you need to do is fine. These materials and supplemental materials are all optional, and you will certainly not be required to know any of this when you get back. So this is just if you want. So finding the cross product of all of these vectors, right? You see, I hope you notice a bunch of ones and zeros, right? So that would be all of these, right? Kind of unit vector things, right? So remember our 3D graph, right? The vector 1, 0, 0 is that unit vector in the x direction, and 0, 1, 0 is right the vector in the y direction. And you remember we called this I, and we called that j. Can you picture what the cross product would be? So let's go ahead and set up and do the math. Remember, the cross product is that three-dimensional determinant, 3 by 3 determinant, if you will. So I is going to be 0. Negative j is also going to be 0. And k is going to be 1 minus 0, yes? So what is the vector that I get out of that? Is technically 0i plus 0j plus k, right? Or of course just k, right? And what does that vector look like graphically? Perpendicular to both I and j. So can you kind of see what's going to go on for the rest of them? Yes, so maybe draw it first. Which two vectors are these? Right, isn't this the j? So what's going to happen when you cross j cross I? Now you learned this in the last video, because this one over here was I cross j. So what happens when we reverse the order, right? So pause and see if you get the same thing I get here. I got negative k for this one.
Thank you, Lenny.
You're welcome, John.
What's going on here?
Yeah.
Well, this vector is k. What's this one? Isn't this negative I? So what does that look like? Negative I would go back this way, right? Into the computer. And k is the unit vector in the z direction. Yeah, so what do you think that is going to look like? What did you get when you did all your mini determinants? Right, hopefully you can kind of just visualize it now with a bunch of zeros and ones. Certainly I'm going to get 0 for I, but J I'm going to get what? J I'm going to get -1. And K I'm going to get 0. So you might be tempted to say, oh, this is -J. What's wrong with that? Good. Remember, when you're doing your actual determinant work, it's the mini determinant times I, the opposite of the mini determinant times. So this one was a 0. This one was a -1, but you had the, and then you certainly had the 0 with K, so this is actually positive J, right? So that's this vector here. Curious, what is D here? This is K crossed with K. So remember what the cross product is. How perpendicular-ish E are these two vectors to each other? Well, wait a second. If we're talking about, oops, sorry. The same vector, how perpendicular is K with itself? Right? So again, maybe you can picture the first mini determinant I'm going to do is here, which is going to be 0 minus 0. The second mini determinant I'm going to be is the I with the K, so I get 0 times this one and 0 times this one. And then the last determinant I'm going to do is the I and J ones, which are zeros. So, right, I get the 0 vector. And that shouldn't be surprising. All right, so this really is just some practice with all of the things that we've learned so far is all that this video is about. So with one new kind of result of what a cross product is, another property. So remember from yesterday's video, we talked about the magnitude of the cross product, right? Remember how I'd forgotten that word? The magnitude of the cross product is the magnitude of each vector times the sine of the angle between them. So that would be here, right? So the sine of the angle between them, where again, if we're talking about the cross magnitude of the cross product, telling us how perpendicular things are, right? So sine of 180 is 0, but the sine of 90 is 1, right? So, and the sine of anything in between there is going to be smaller than 1. Now check this out. What happens if I draw a parallel vector to the blue one and do tip to tail, and then a parallel vector to the red one, tip to tail? What is that shape? A parallelogram, right? So a parallelogram, if you remember from geometry, right? Four-sided figure. What's the area of the parallelogram? Base times height, just like a square, just like a rectangle. It's just, but the height is harder to find with a square and a rectangle, correct? So if I determine, though, if I call the red vector A if I call this vector A, and I say that that's the base of this parallelogram, its magnitude times the height is the area, yes? So now how do I find the height? To find the height of this parallelogram, I need this line drawn. Do you see this dotted line right here? And I have a little mini triangle with theta in there, right? So isn't it true that over here, isn't it true that the sine, oops, sorry, slate is a little weird, that the sine of that angle, theta, is the height over what? The length of the blue vector. Well, what happens if I solve that for h? If I solve that for h, don't I get the height of the parallelogram as the magnitude of the blue vector times sine of that angle in between the two vectors? And now what if I do some substitution here, right? What if I take what h is equal to and plug it in there? Oh, snap. The magnitude of the cross product is the same as the area of the parallelogram enclosed by the two vectors when I do tip to tail with each one. Mind blown. Now you're probably thinking this is a ridiculous thing for figuring out the area of a parallelogram, or if I actually want the area of that triangle, I could just take 1/2 of the magnitude of the cross product. We do this an awful lot in multivariable calculus though. We really do use this an awful lot. And the whole idea of the parallelogram, I know it's not going to make any sense now why we would need it, but you do need it. Crazy though, right? Another property of cross products that I referred to yesterday, and you saw a little bit in the video that you watched yesterday, is about this right-hand rule. So thinking about the right-hand rule, if any of you, I don't know if in an AP Physics 1, you've dealt with this yet, cross products, but you certainly will in IB Physics and AP Physics C. So I have another little video for us to watch about the right-hand rule, and this is actually how I do. There's a couple different ways to use the right-hand rule, but the idea behind your thumb excuse me, is that your thumb is going to not give you the magnitude, but it's just going to point in the direction of the cross product if you lay your fingers of your right hand appropriately with the first finger on the first vector of the cross product. So my first finger would lay on vector A if I was crossing A cross B, but my first finger would lay on vector B if I was doing B cross A, and then my thumb would point in the direction of the cross product. So let me play this video for you.
We're going to do a couple more examples of finding the vector cross product. Suppose that I give you these two vectors, A and B, which both lie in the plane of the, look, it's my hand, which both lie in the plane of the page, okay? So there are A and B, and you want to find the direction of A cross B. To find the magnitude, you would do A times B times the sine of the angle between them, but we just want to find the direction right now. And to do this, we're going to use the right-hand rule, but first we can use a little bit of logic. So first of all, logic says this: whatever the direction of A cross B is, which let's call that C, A cross B, call that C, it has to be perpendicular to both A and B, or perpendicular to the plane of the page. Well, there are only two directions that could be, right? What that means is that C either must point straight out of the page, or it must point straight into the page. And to figure out which one of those two directions it is, what we're going to have to do is we're going to have to put our fingers along A. So there are two ways to do that. You could either put your fingers along A this way, or you could put your fingers along A this way. And you have to do it in the way that will let you swing A down into B, like it was a little hinge. So if you try that, notice, if you do it this way, it's the wrong way, right? You'd have to swing all the way the long way around. If you want to just simply fold A into B, the way to do that is to put your fingers this away, then you can curl them down this way. Notice when you do that, your thumb is pointing into the page. So therefore the answer is that C is into the page. And actually, I got marker on my wall. Actually, the way we represent that is that's represented into the page is represented by a little X with a circle around it. You're supposed to think of it like the tail feathers of an arrow that's pointing into the page.
Okay. And that actually, again, I don't know how much you've done this if you're in AP. I know some of you are in AP Physics 1, but that notion of that circle with the cross indicating that the cross product is going into your page versus coming out, which I believe is just a little dot if it's the other way coming out, but I'd have to call in my physics expert, Mr. Getz, and verify that. Okay, that's really it for little extensions on the stuff we did before. So now there is a handout with a practice of everything we've done since Friday. Again, not required, not tested, not not designed to give anybody stress. Just an activity if you want to do it, if you choose to do it. I mean, I'm a nerd, so I do like doing math while I'm at home, but I understand perfectly well that other people might, and again, I certainly don't mean to cause anybody stress by like, oh my gosh, I need to get caught up or stay. Please, please, those are the least of our worries. This is only a diversion if you want. So this handout is available on, I don't know if you picked it up or if it was one of the ones we picked up, but it is also on our Canvas website, and it says Unit 9 Vector Practice, I think, and it should be number 3, both in the Solutions and in the Handout folder. So I'm going to switch over to my Word document where I've got this. So I'm not certainly going to do all of these with you, but I wanted to do a decent amount of them on the first page. And then like one of each of the other sections. So the beginning here is just asking you for some vocabulary and some wrap up of what we were just talking about. And it's important that you do realize that the cross product of two vectors is another what? Right. A cross product is a vector, and that differentiates it from the dot product, where the dot product is a number, a scalar. And what's special about the dot product? Yes, perpendicular to both. And then number 2 is what I just took you through. The magnitude of the cross product of two vectors is equal to what of a parallelogram? If you put U and V as adjacent sides of the parallelogram. And then something your homework is going to ask you to do later also, don't forget that 1/2 the magnitude is the area of the triangle associated with U and V being the sides of a triangle, right? And then just closing the end of the two vectors, right? Because it's half of the parallelogram. And then we just had a video to, right, kind of explain the right-hand rule. So to explain the right-hand rule, all I'm looking for you to say is, right, that firstly you are using the right hand. That's number 1. Number 1, you're using the right hand. Number 2, right, that you're laying fingers on the first on the first vector of the cross product. And then 3 3, you need to curl your fingers in the direction of the second vector. So for number 4, when they ask you to look at the two vectors below, u and v, and if you put the paper down flat, they're asking you, does the vector, and before I finish reading, right, I want to make note of which is the first vector, u. So lay your fingers on u, and if you lay your fingers on u with your pinky down on the paper, your thumb would point up at the ceiling, but you couldn't curl your fingers towards V, right? You couldn't do that. So you need to turn your fingers over so that it is your forefinger that is laying on U, and then you can curl your fingers in the direction of V. So since U was the first vector in the cross product, in order to curl, start with V and curl towards V, start with U and curl towards V, my thumb would be pointing at the floor. So what would happen, right, and the only explanation for that to me is the right-hand rule, right? That's all I'm going to say there. The right-hand rule is the reason my thumb would point. I'd like to go out on a long walk with them, too, but I just need to wait, a little bit.
Yeah, we should like tennis now while sunny and nice.
Right-hand rule. So, but what if I asked you, then that should beg the question, what if I asked you about V cross U?
I have other questions for you.
Right? If I asked you about V cross U, you would lay your pinkies, right? If you lay your finger with your pinky down on V, and then you could curl towards U, right? And where would your thumb be pointing? Right? That would then be the ceiling, right? My thumb would point at the ceiling. Right, so again, it's the right-hand rule is nice for trying to picture what the cross product is doing, especially for vectors that are lying, right? It's kind of easier to picture if somebody orients me on an axis, but if I've just got random vectors, I'm not exactly sure. All right, so the next part here, I don't feel like I need to do any of these with you. Determine the cross product of the following vectors. We practiced some of those nice ones on the warm-up, and we did those yesterday. And again, check my key if you want to see if you're doing the work correctly. But I did want to go down and do number 8 with you, because 8 was something a little bit new, right, that we did today, because it says determine the area, but it says the area of the triangle, not parallelogram. So remember, we have to take the half of the parallelogram area that we get. And annoyingly, they gave us these, right, they gave us the vectors in these forms. So the first thing I have to do, I'm just going to, for convenience sake, I'm going to name each one of these. So I'm going to name this vector A, B, and C. Yeah? I can in a minute. And I'm going to say that vector AB an old objective. Vector AB is, right, subtract the B components from the A components, and I got 1, 2, 2. Check my math on that. So there's vector AB, and then I did vector AC, right, because I want to join at A and go to AC to create these adjacent vectors. And I did the components of C minus the components of A, and I got -1, -3, 4. Again, check my math on that. Then I did the cross product of these two. Ooh, that's quite light, isn't it? Sorry about that. I was trying to just get thinner. When I did that cross product, again, you can practice that cross product. But I got 14, 6, and -1. I think I will go back to my red. Excuse me. And then I took the magnitude of that. Which was the square root of 14 squared plus 6 squared plus 1 squared. And I got the square root of 233 out of that. But that is the area of what? The magnitude of the cross product is the area of that parallelogram. Oh, that's a terrible parallelogram. Oh, my Lanta. But I want the area of the triangle, so I just take a half of that. I didn't get the decimal approximation to that, but I could, right? If this would open. Never mind, not important. I'm sure you can type that into your calculator. All right, on the next page, again, most of this is review, right? So they just want to determine whether A, B, and C, D are equivalent, justify your answer. So all I need to do here is compute A and B. I got 2 and 3 for AB. And for CD, shocker, I got 2 and 3. So since they're equal, yes. I don't know that I really needed to say justify, right? I just wanted to do one of those to show you that the word, I didn't want the word justify. Usually when I say justify, I need a little bit more than that, but I didn't write this worksheet, but I think it's pretty good. I just didn't want you to worry about that word justify. So for this one, again, this is practice, right? So you decide what kind of practice you need. I did want to say, you know, look at a problem like number 8, right? And that's just good practice, making sure, firstly, you can find AD and then multiply it times 2. So I did 2 times 2 comma 1, and I subtracted that from 5 times 3 comma -4. So when I did that math, that vector, resultant vector in component form was negative 11 comma 22. If they had asked me for a sum of unit vectors, I would write that as negative 11, and they didn't, but just in case, I could write it like that. But they did ask me for the magnitude. So the magnitude of this vector is the square root of 11 squared. I don't need the negatives, right, if I'm squaring. Plus 22 squared. And when I pushed that into my calculator, I got the square root of 605. This time they gave me vectors in, right, already in component form. I don't have to put them in component form. So I just wanted to make sure that you were, right, so to do a problem like number 13, negate u. So negative 2, negative 6. And then it's asking me to negate v. So I'm going to write plus and then negate. Right? Isn't it the same? Subtraction is the same as addition of the opposite. Well, just, right, and then plus w. And if I did my math right, I got 4 negative 10 out of that. The next group of problems was asking you to practice unit vectors. Right? Find the unit vector in the same direction as the given vector. So this is negative I plus j, which is kind of funny, right, to ask for a unit vector in that instance. But what they're asking you for is, right, look for component form, which would be negative 1, 1, is how I think of that. Find the magnitude of that, which is super easy, right? Square root of 1 squared plus 1 squared, aka the square root of 2. So the unit vector then would have the components negative 1 and 1, but each one of them divided by the square root of 2. Gee, those numbers look familiar. And then 18 and 19, also, right, old news. We've done a problem like this before. So number 19, but it's dealing with the angle. This is asking you to remember that in component form, you need to take the magnitude, and for the x component, you take the cosine, the horizontal component of 160 degrees. And then 20 times the sine, or the vertical component of the vector, 160 degrees. And when I punch this into my calculator, making sure I'm in radians, I got negative 18.8 and 6.8. So on the last page, making sure you're okay with finding the magnitude and the direction of the vector. Remember what that means? Direction of the vector? Right? Direction of the vector means you're finding theta. Yeah. And theta, remember, is in standard position. So what messes kids up here is stuff from, right, AAF and this year, early this year, first semester. Right, so the new stuff here, you won't have any problem finding the magnitude of this. Hopefully you realize that's a Pythagorean triple right there, right? So the magnitude is equal to 10. But where is the vector? What quadrant is vector 6, 8 in? right? 6, 8, isn't that in quadrant 1? So say let's pretend 6, 8 is somewhere around there. Since I'm in quadrant 1, I am just thinking about this angle theta. There's my theta, right? So there's a lot of things I can do to find that. And since I'm in quadrant 1, I have no worries about whether I'm doing inverse sine, inverse cosine, inverse tangent. I like, in general, to work with numbers I've been given rather than numbers I find. So I mean, even though using 10, I don't think I made a mistake. I punched into my calculator and I got 53.1 degrees, which seems to be a reasonable, right, given my picture. It's nice to be able to, if you don't draw these, at least, right, picture what quadrant I'm in. So I'll leave the magnitude for you, but I will say, I'll give you, like for each one, since negative 2, 5 was in quadrant 2, I used inverse cosine. For number 22, where your x is positive and your y is negative, that was quadrant 4, I used inverse tangent. See, I was going to get the negative there. Again, I don't care what you use as long as you get the right angle. And I can measure in the negative direction here. So for 21, I got 111.8. Because the cosine, I found the magnitude was the square root of 29, so I used negative 2 over the square root of 29. And for 4, I used the inverse tangent of negative 3 over 5. And I got negative 30, I can't read my own writing, what is that? Negative 31.0 degrees. Now for 23 though, 23 was in quadrant 3. So I just did something different, right? Again, there's lots of correct ways to get the correct answer. I just wanted to show you a couple different ones. So for this one, I was in quadrant 3. Right, there's my angle. There's my vector. I actually found this angle here. I found that angle, which is not the angle that I want, but I used inverse tangent to get that. As long as I have a picture and know what angle the calculator is giving me, and I didn't bother with negatives, I just did 24 over 7. And I got 73 degrees. Just giving you different ways to approach the problem. So I got this actual angle here, almost as if this was a triangle, right? If this was some triangle, I got this angle here, and that angle was 73 degrees. Well, what angle do I want? Theta, which is measured in standard position, I could go 180 degrees plus 73, or if I really wanted to, I could do the negative one as well, but I kind of like to keep the positivity going. So I added 180 here, and I got 253. Now looking at 24, just how do I approach that problem? Find a vector with the same direction, but with a magnitude of 20. So they're dictating, we kind of did this with the work problems, they're dictating that the magnitude is 20, and when I look at negative 3 and 4, I know that magnitude is not 20, right? That's a 3, 4, 5 triangle. So my first step is to get a unit vector. If I take my vector and make it have it a magnitude of 1, so since I know my magnitude of negative 3, 4 is 5, my unit vector then is -3 over radical 5, comma 4 over radical 5. That's my unit vector. What is that length? What is the magnitude of that vector? Well, it's 1. That's the whole idea of making it a unit vector. And I want to multiply that magnitude by what? Oh, my bad. I wrote root 5 here, didn't I? And this is 5, not root 5. Silly girl. Right? And of course those 5s will cancel there, so I end up with -12, 16, because all of those were such nice numbers. (25) and 26 are your favorite problems, aren't they? Aren't they your faves? Right? 25 and 26, there's those bearing problems. Okay, so bearing problems, you just have to remember where you're being measured from. So I have an airplane. Oh, it's terrible, isn't it? My airplane is flying at a bearing of 200. So there's 90, 180, so 200 is about there, right? Oh, it's 200 degrees, my bad, but the speed is 500. I meant to write 500 there. But this bearing is 200 degrees. But they want the component form of the velocity of the plane. Right? So to find the component form, I am multiplying 500 times cosine of an angle, and then 500 times the vertical component, which would be the sine. The problem is that's not 200, right? Because in this definition, the theta, the angle that you need, is, how thick that is. The angle that you need is theta, right? So well, what's theta? That's 90. And how's that? That's what? 10 more. So isn't this negative 110 degrees? So when I punch this into my calculator, I got negative 171. And negative 470. Right, so that's actually what's happening to the plane. The component form of this vector. Now the next one is a combo, which I think you're used to, right? They're giving you information about both a plane and the wind. So this is my airplane and this is my wind. Right? So what's going on? So a company's heading with a bearing of 300. So I need to go around to 270, go all the way around to 270 plus a little bit more. And there's my plane. How fast is it going? Hold on, sweetie. I'm almost done. 400. Now, I think this is a little bit of a mean phrasing. So, and I want to reassure you that if you get this phrasing wrong on a test, remember, we don't really care on a math test if you can figure out what from a wind blowing from the southwest as or east or whatever. So just do something, right? So I wouldn't phrase it like this, but if it is blowing from the southwest, that actually means what effect is that on your airplane, right? Northeast, which is a little bit mean, I think, right? If they're going to write the word southwest, I first drew this problem as down and to the left, south and west, but from the southwest, meaning if I'm coming from the southwest, then the effect on my plane is pushing it northeast. So what's going on here? How fast is this? This is 100 miles per hour, right? And what is now from the southwest, the nice thing in it that is very nice for a compass thing, right? What is this angle? I don't have to worry about bearing. This is 45 degrees, yes? So they want to find the actual ground speed and direction of the plane. So that means I have to add the plane as well as the effect on the wind. So the wind, not a big deal, right? The wind is 100 cosine 45. And 100 sine 45. But what's the deal with the airplane? What do you have to do with the airplane? 400's no big deal. Cosine's no big deal. The 400's no big deal. And the sine's no big deal. But what angle do I have to put in there? Right? The angle, theta, right? 90 plus what? Exactly. Right? How did I get that? Well, if this was if I was going from bearing, my bearing was 300, so this little part here had to have been, I went all the way to 270 and then to 330. 330 meant I went 30 more. So this part needed to be 60, and I went 90. So that's how I got the 150. So I just need to add, oh, what is the deal with that? I need to add those together. And what I did, I got about negative 275.7, and I stored that in alpha A. And then approximately 270.7, and I wanted to store that in alpha W for wind, but I didn't. I stored it in alpha B. Then I did the magnitude, so on my calculator, I did the square root of alpha A squared plus alpha B squared, and I got 386. And what am I in? Miles per hour, right? Am I done with the question? I don't think so. They asked me about the direction of the actual direction of the plane. So I know the direction it was pointed and I know the direction of the wind, but now what is the resultant direction? So that's asking me for, right? I can do theta. So here's again where you, again, there's multiple ways to do this problem. So I drew the resultant, like a picture for my resultant. Let me take this away for a second. So negative 275 and positive 270 is something like this, right? So I found this angle right here, as if I had a triangle. So as if I had a triangle made with the negative x-axis, I found this angle, and I used that with the inverse tangent. So in my calculator, I did inverse tangent, and again, I didn't deal with negatives of that 270-ish number. Positive. So if I was using, I would do negative, well, I would do alpha b over negative a, because I don't need, I'm looking just for that positive angle of that triangle. Right? So that's given that this angle right here. And that angle was 44-ish degrees, which makes sense, right? So I got 44.5 degrees. But this question was asking me about the direction of the plane, and it was talking to me in bearings, so I've got to talk back to it in bearings, right? So I need to measure, they want this angle measured from the north. So that's 90, 270, and then plus how much is the bearing?
She moves so easily. Jeez.
Are you doing virtual yoga in there?
Yes.
Nicely done. Is that Kira?
No, it's softball.
Oh, hi, softball.
Is she stuck on Luke? She looks like a fake person. Is that animation? Oh, so we need to keep up again? Oh god, I can't do this one. You know.
So there you go. I was asked for the actual ground speed, which I found here, and the bearing of the plane with the effect of the wind.
Are you recording a video lecture?
Yeah? Say hi to my students.
Hi, students.
So that is Devin, home from college. Her and her softball seniors are all doing yoga together, and they say hello to you. So hopefully you are doing yoga. We are also going to go out and play some tennis, keeping our social distance from everyone. We have taken some long walks with our dog Duke. We have played some games, Seven Wonders. If you haven't done that, I suggest if you have that, Seven Wonders is a really nerdy but cool game that we've played here. We've played
Oh
piano
wow, he's good.
and sung some songs, and done some baking.
Ow.
So I hope you all are doing whatever you need to do to relax and be happy and healthy, both physically and emotionally. Know that I am thinking of you, and that I hope to see you soon, and don't know when that is, but whenever it is, it will be nice to see all of you. And I want to wish you and your family all the best.